for the start. Hi, Bea. Um, Welcome to the lesson on inverse functions. I guess I'll just get started. Uh, so on inverses, just got a nice heading going. All right, so let's just start with a bit of introduction as to why these functions are even a thing. So last week we covered normal functions, and we said that functions take inputs Hello? Can you hear me? It seems Escom has, or Telcom has let me in the dark. My internet just disconnected. Um, Hello, Nkhafa? Hello? 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 Hello, are you here? Sorry about that. Telcom left me in the dark here. Uh, they just turned off my internet for some reason. Um, did I get to explain any of this, or do you just want me to just start again? Because I can just start again. I don't know when it cut off.
Just start again, Taro.
All right, sorry.
Yeah.
This is all of this. Or actually, I don't even need to. I can just. All right. Okay. So what I was saying was, from last week, we did functions, and we said that every function maps our inputs are in our domain to our outputs in our range. So the reason why we need inverses is we want to find a way such that we can map these same outputs that we get from our function back to inputs. So you can see in the real world, you can probably like think about how this will be useful for. An important thing to note as well for inverse functions is that the inverse function f minus 1, this is how we notate an inverse function, but this is not necessarily equal to 1 over f of x. So don't in your test write f minus 1x and then just write that as 1 over f of x. While it's true that x to the minus 1 is equal to 1 over x, this does not hold in this notation. So just want to quickly show just a visualization of how these inverses works. Let's say I have a little bubble here, and this is my domain. So these are all the numbers that are the inputs for my function. So let's say -2 to 3. Let's just say this. And then we have our little function f of x. And let's say our function is x squared. Now, we take this number, we plug it into the function, and what we get is another little bubble. And this will be our range. So let's check what will be in our range. If we take -2, we square it, we get 4. So this -2 squared equals 4. That's how we got it. And now we do the same with 2. And we say 2 squared, we also get 4. So I don't write 4 again, we already have the element 4 in our set here. Now, it's already important to see that 2 points in this domain can give the same answer here. We'll just store that information for later. Now we do the same for 3. 3 squared, 9. So now we see to go from our domain to our range, we just apply f of x to our inputs. So we take every element in our domain, we apply the function to it, and that gives us our range, our outputs. But now, what do inverses do? They just do the opposite. F minus 1. Now, what's important here is, obviously, we all know x squared. And from just solving equations and knowledge we've gained from the past, we know that the inverse function will just be the square root, right? So, if I take the square root function, let's say 9, square root 9, what is that? 3. You can see here, 9 becomes 3 if we plug it into our inverse function. Now let's do the same for 4. let's take square root of 4 is equal to plus or minus 2. This is important because minus 2 squared is equal to 4, 2 squared is equal to 4. So we say minus 2 and 2 belong to this one element here. If we take the inverse of 4, we get minus 2 and 2. Now this is also an important thing that I'll demonstrate later, is that while this may be a function, the inverse may not be necessarily a function because there's one input and it's giving me two outputs. All right, so let's just get on to more application type. So let's start with finding, what you should be thinking when there's an inverse question. You should be thinking of the stuff I'm going to tell you now. If they say either find the inverse, so in the exam if they say find the inverse of an equation, that's what you know what to do. Or if they say find, let's say, f minus 1, of course, also the inverse. But now what they can also say is reflect in the line y equals 2x. And this is very important because this is essentially what it means to find an inverse function. Finding the inverse literally just means reflecting in the line y equals x. So some keynotes here. We can say it's finding the inverse, find f minus 1, or reflecting in the line y equals x. And to find a function, all we're going to do, if you remember from, I think, grade 9, reflecting the line y equals x just means swapping x and y, pretty much. X and y. Now, another important thing to note is all x points on our graph on f will become y points on f minus 1. And the same works for the other way around. All y points on f become x points on f minus 1. Now, I'll demonstrate this a bit later. Let's just start with a common question. Let's say for straight lines, how do I find the inverse of a straight line? Let's start with let's say fx is equal to mx plus c. Now, this is just your basic definition of a straight line. And what we want to do when we're finding the equation given in this term of the inverse, we want to swap x and y. Swapping x and y. So all that give us, this is technically y, right? Our outputs. So if we swap x and y, this just becomes an x, and this becomes a y. So we have x is equal to my plus c. If you follow, this was a y, becomes an x becomes a y. I'm literally just swapping the variables x and y. But this doesn't make much sense because we don't write something, okay, the input is this. We don't know any function that says x is equal to, or x is equal to y squared, x is equal to my plus c. We only know the functions in terms of y equals. So writing it like this is not actually correct for how they want it in the exam. What you're going to have to do is you're going to have to solve for y by getting this alone on one side. So what you do is you just say, all right, x minus c is equal to my. And here we can just see y equals x minus c over m. So for a straight line with y equals mx plus c, the inverse will be the form y equals x minus c over m. You don't necessarily have to memorize that a straight line becomes this with these variables. I feel like it's way better to just understand how to do this, and then because this helps with application in other questions. Now, let's just do an example quickly. Let's say I have f of x is equal to 2x plus 3. Now, first thing I think about is what is this going to look like? Let's draw a graph. Remember to always, when you're drawing axes, label them. You lose marks if you don't x, y. Now, this is going to look something like this. It's going to have a y-intercept at 3, and it's going to have an x-cut at minus 3 over 2. And let's just draw this line in. Okay, so 3 here. Now, remember I said reflecting in the line of y equals x. This is just a straight line. So we can actually show how that will look. We just have a line going right through. And this is our line y is equal to x. Now, in reality, this goes all the way down and cuts it. So you can probably intuitively just see what the inverse is going to look like. If it's reflected on the line y equals x, what it looks like here is what it's going to look like here. But let's use our method, because that's going to give us the most marks in the end. So we say we have y equals 2x plus 3. So swapping x and y, we have x is equal to 2y plus 3. And then solving this all the way down, we get y is equal to x over 2 minus 3 over 2. Now, this is another straight line. And this straight line has an x cut at 3 and a y cut at minus 3 over 2. All right. So what's really cool to note here is that, remember I said every point, all x points on f become y points on f minus 1. Now let's actually look at this. Here our x coordinate was minus 3 over 2. Now if you look at our y coordinates of our inverse, it is minus 3 over 2. And the same for all y points. The y point here was 3 on our function. Now the x cut becomes 3 of our inverse. And this will look something like this. So there you go. There's your f of x. Here's your f minus 1x. That is really as difficult it gets for straight lines. Just remember to show as much working as you can. Remember to label your axes, depending on, of course, what they ask you in the question. Now onto the next one, next section. Let's start with the parabola. This one is just slightly more difficult because there are a bit of just intricacies going into this one. So what's important when finding the inverse of parabolas is remembering which formula of the parabola to use. Now, if you remember, the parabola has two formulas. One like this, plus q. Sorry, that's q. Plus q. Or y equals ax squared plus bx plus c. Now, when we're finding the equations of an inverse of a parabola, we do not want to use this. This is a lot more difficult. You can imagine saying, imagine you have x is ay squared plus by plus c. That's going to be very difficult to solve for y in this function because of the y squared plus by. So we don't want to use this. This makes it way too tricky for us. What we want is we want this one. Because notice here that the variable y and the variable x only appears once. So when we're swapping x and y, it's going to be a lot easier. So let's just take an example. It's going to be easier. Let's say f of x is equal to 2x minus 1 squared. Let's say plus 2. And I'm just going to graph this, just so we have just a reference image quickly. So this is a parabola, of course, with x coordinates at 1, x minus 1, so it's going to be on the plus side. X is 1, and it's going to have a y coordinate of the turning point at 2. A is positive, so it's going to look something like this. In the test or exam, you're going to have to find this point here, but I just want to show just a general shape for now. Now, to find the inverse, nothing really changes. All that we do is we swap x and y. You're more than welcome to write this in your exam, just swap x and y. So this becomes x is equal to 2 y minus 1 squared plus 2. Now, we can do a bit of algebra here, and we can say this is just x minus 2 is equal to 2 y minus 1 squared. All I did was subtract 2 from both sides. Now, this becomes x minus 2 over 2 is equal to y minus 1 squared. All I did, again, divide by the 2 on both sides. Now what we can do is, since this is squared, let's square root both sides. But thing to remember, when we square root both sides and we introduce a root into our equation later on, we have to make sure that we write a plus minus root. X minus 2 over 2 is equal to y minus 1. Now you can just see that y is equal to plus minus root x minus 2 over 2 plus 1. And this is your equation of f minus 1, your inverse. Now if we want to graph this, I find it personally a lot easier to just, when graphing it, using this information that we have here. Notice that this is going to be the point 1, 2. Drawing our line y is equal to x. Like this. Y equals x. And then saying, if the x coordinate of the turning point is 1, what is the y coordinate of the turning point of my other one? It's going to be 1, because they swap. So I have my line here, y equals 1. Actually, let's do this in a different color. Mr. Blue. Y equals 1. And now we have, just fill this in. So the x coordinate of the turning point becomes the y coordinate of the inverse. The y, obviously, other way around. Let's draw a line. X is equal to 2. Now, this is just going to have a point here where they intersect. And we're going to draw something like this. So this is our function f, and this is our inverse function. Now, just remember that you're going to have to label this point here, which will just be this point the other way around, over here, and always label your turning point. Since this is 1, 2, this will just be 2, 1. It's as easy as that. Now, the one trick with parabolas is we want functions. Notice that this is definitely not a function. And the reason it's not a function is because I can draw a line like this, so like this. And what you notice is that for one x value, I have two y values. And this doesn't work for functions. We don't want this. This is our same issue as earlier, where we said the inverse of the input of the inverse gave us two values. Remember, if we go back here, we saw that when we square rooted in 4, this happened, right? In reality, this is also plus minus 3. So we can actually see that this actually happens to all of them. And what do you notice about x squared? Well, y equals x squared is a parabola. It's what we have here, just shifted a bit. So what we have to do in order to make this a function is we have to restrict the domain of f. So we have to restrict for what values of x. Restricting the domain means restricting the values of x, the inputs of our domains, such that this will exist. So we can choose, obviously, to the right of this point. If it's to the right of this point and to the left of this point, it gives an issue, because the reason why there's two values is because this part goes up and this part goes down at the exact same rate. So what we can do is we can just say, when you're doing this in the test, you say either x is less than or equal to 1 or x is greater than or equal to 1. You don't have to do both, just pick one. Because the moment you say, all right, this only exists for x less than 1, then you only have one of these lines. And same for this. So that's really important, restricting the domain of x, of f of x. The reason I choose 1 is obviously this is the x coord of your turning point. So in a test, if they say, for what value of x do I restrict the graph so that the inverse exists, you just say x greater than the x coordinate of the turning point of the original graph. Now, I just like to, before we carry on to the next section, if we could all just do a question together. Have a picture here. Nothing to paste. Here we go. Let's take this. How do I get rid of this? I don't want this floating around. Well, whatever. We'll have to deal with it. All right. Let's just do this question. I'll give you a couple of minutes to do this first question. Sorry about that. All right, I'm just going to start with 4.1 so long. Let's go 4.1. Now, when I do a question like this, what I like to do is first just read all the information and then just try to link in my brain everything that makes sense. So what do you have here? In the diagram below, the graph of fx is equal to ax squared is drawn on the interval x less than or equal to 0. This, we know, is a parabola, just because of the form. Ax squared is parabola on the interval x less than or equal to 0. So we'll see here, the image only exists when x is less than or equal to 0. The graph of the inverse of f is also drawn for p minus 6 minus 12 is a point on f and r is a point on f of inverse. All right, so the inverse of f is this one, they give it to us, and f ax squared is equal to this one. So they're saying f passes through the point minus 16 minus 12, and r is a point on f minus 1. All right, so now let's go to 4.1. Is the inverse of f a function? Motivate your answer. Now we'll see here, the issue that we had arising here was it's not a function because we have to restrict the domain. But if we notice here, they've already done that for us. So is f minus inverse of f a function? Let's look at it. For every one x, is there only one y on the graph? So if I take a line down here, there's only one f. If I take a line down here, there's only one y. Line here, only one y. Line here, only one y. Line down here, and we'll see that this continues all the way to negative infinity. So for every one x, there is only one value on the inverse. So we say yes, it is. It is a function. And we say because every 1x only has one y value. There are many different ways you can word this. Maths is not too finicky about how you answer these types of questions, but this is two quick marks. It's a function because every x there is only one y value. So for every x in the domain, there's only one y. Now for 4.2, we say if R is the reflection of P in the line y equals x, to make it easier for us, draw a line y equals x. And it's going to look something like that. If R is the reflection of P in the line y equals x, write down the coordinates of R. So they're saying these points actually have something to do with each other. There's a reason why they give us this. And remember earlier, I said the x's become the y's and the y's become the x's. So if the point on the graph is x is minus 16 and y is minus 12, that works the same way here. R will then be not minus 6 minus 12, but just minus 12 minus 6. If the logic works for x cuts, surely it works for every point. If a x on the f becomes a y on the inverse, and if p is x value is minus 6, then r's value is minus 6. So in essence, to get the reflected points, you're literally just swapping x and y. Yes, you could say because of the vertical line test, but sorry, I only saw your question now. Yeah, vertical line test, obviously, you draw a vertical line, but what the vertical line test implies is that for every one x only has one y value. So I would say the vertical test, you can say because of the vertical line test, I can see that for every one x value, there is only one y value, because that's what the vertical line test is in essence testing. If R is a reflection of P in the line, oh, we've already done that one, sorry. 4.3. Calculate the value of A. So A is here, fx is equal to ax squared. So let's see what we have now. We've just calculated that in 4.2, R is the point minus 12 minus 6. There's not much else we can really note. We know that 0, 0 also passes the point, the origin, 0, 0 value. So this is just checking what information we have and trying to substitute in. Because there's really only one unknown here, you just sub in a value. So let's just put minus 12 and minus 6 into this function. So the function value at minus 12 is minus 6. So that means minus 6 is equal to a. Wait, actually, sorry. We're not looking at the point minus 12 minus 6. Sorry, my bad. We're looking at the point minus 6 minus 12, because the inverse of f passes through the point minus 12 minus 6, but f passes through minus 6 minus 12. Sorry, my bad. So this goes through minus 6 minus 12. And we have that minus 12 is equal to a times minus 6 squared. And you have minus 12 is equal to 36a. So we have a is equal to minus 1 over 3. All right. All right. Now let's do 4.4. If I say, do you want some time to do 4.4, or have you already? I'll scroll up a bit. Alright, I'm just gonna give the answer quickly. So this is this is ironically the easiest part of it, and it's with 3 marks. This is literally just what we did earlier. We said swapping, or say f of x is equal to minus 1 over 3 x squared. What do we do when we're finding the inverse? We swap x and y, and we say x is equal to minus 1 over 3 y squared. Now, this is just algebra. We say, how do we get y alone? We can say, sorry, this just becomes minus 3x is equal to y squared, and square rooting both sides, we get y is equal to plus minus the square root of minus 3x, right? But this is a bit weird, because what's the square root of a negative number? It's it we can't really define it. And if we notice here, oh sorry, not here, here. The function does not exist for y or x greater than 0, right? This function does not exist for y greater than 0. So we say does not exist for y greater than 0, and actually also x greater than 0, because we cannot have the square root of a negative number. Square root of minus 3 does not exist. So if x is 3, if x is 1, doesn't work. That is why we restricted it to less than or equal to 0. And we have that the answer is, so f minus 1x is equal to minus 3x for x less than or equal to 0. Now, what's important is most of your marks you're going to get from this, and this should not really be the biggest of your worries. If you can guess this does clear it up a lot and it's going to give you a mark, but 2 of your 3 marks you find from here. So even if maybe this is a bit shady for you, it is a bit weird because of non-existence, but most of your marks you can get from here. So don't, when you see the question, that's an important exam writing skill. Let's say you get stuck let's say you get stuck here and you say, oh no, I've never seen this before, I'm just lost. That's fine. You've got your marks for the things you understand, and then it's important to just move on. That's really important skill to learn, because the 1 mark that's gonna confuse you probably here is not worth it when you can be doing question 5, which will be on functions, which is worth something like 8, 9 marks. So sometimes it's important to move on, get back, and then maybe when you get back, this makes a lot more sense anyway. So that's just in the exam, something doesn't make sense, but you've got most of your marks. Safer just to move on. Right, let's go to a next section. Are you happy with that, Bea? You happy with parabolas? Okay, I'm just gonna assume you're fine with it. Just let me know later if you want me to come back to it or something. So let's go on to the next very fun section in inverses, and this is logarithms. So let's start with the definition. A lot of people get confused by log because it's a new thing to them. Log is just a function, much like square root or a square. It's literally just a function. What people, what confuses people is the notation. Now, what this means is, what do I raise b by to get to x? So log, let's say, what do I raise 2 by to get to 8? What this means what do I raise 2 by to get 8? So 2 to the power of what is equal to 8? Equal to 3. Log 2, 8 is equal to 3. On your calculator, you have the log button on your calculator. 2 of 8 is 3. So what does it mean if 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 this is the logic? If I see a log, I can in my brain say what log base 2 8 means. It just means 2 to the power of what gives me 8. And the answer to 2 to the power of what gives me 8 is 3. 2 to the power of 3 gives me 8. So the fact that that is a thing, this implies these implies backwards and forwards that b to the power of y is equal to x. This is a very, very important relationship. This is the mathematical interpretation. This is the English representation of what it means. If you can, in the exam, find clarity and break down this into English, you should have no problems with logs. Once you can read log like this, it's a lot easier. So a favor you can do for me is whenever you see log in a question paper or when you're writing down log, read it as 2 to the power of what is equal to 8. That makes it a lot easier. And then remember, this relationship is literally just this, but in maths. 2 to the power of what gives me that. B to the power of what gives me x. B to the power of this gives me this. All right. So now that we have this basic definition out of the way, let's go to the exponential inverse. Let's go to the exponential. Let's say I have my f of x, and this is equal to, say, ax. So what this means is I'm taking numbers in my domain, I'm taking x's, and I'm saying, okay, I'm taking a, let's say a is whatever, and I'm raising this to the power of x. So 1, a to the 1 will just be a. 0, 1. A squared, a squared. When x is 3, this is a cubed. When this is 4, this is a to the 4. And this carries on for all x values. So, if I read this as the function that raises something to that power, just intuitively you're going to think that it has something to do with logs. So let's check. Let's swap x and y. Then we have x is equal to a to the y. This looks just a bit familiar to something, doesn't it? Because this is this. If I have x is equal to a to the y, then that means that log ax, right? So I have that f minus 1 x is just log a to the x. So this is how we get from this step here to this, to the logs. And this makes sense because an exponential obviously has exponents. If a log tells me what exponent I need to raise it to get a certain number, then of course mapping outputs to inputs for an exponential is going to be a log. Now, what you can see here is a very easy shortcut you can do. Notice that this is just this. So if they give you fx is equal to a to the x, the inverse will always be log a to the x. Now, what if f is equal to log a to the x? What is the inverse? It's also just going to be a to the x. So this is a very neat trick. Log a to the x, the inverse is a to the x, inverse log a to the x. Let's carry on then. So let's give a bit of an example. Let's say I have y is equal to 3 to the power of x. This is my f. My inverse is just log 3x. Now, an important just a little note here, you can just memorize these, is if f is then a half, y is equal to a half to the power of x, this will just become log half x as well. Nothing changes. Now, if a is less than 0, so if this is negative, you can just write it, the inverse minus 1 is just log a minus x. This you can prove using the swap x and y, but you can just remember this. If a is negative, what changes is this. It doesn't become log minus ax, it becomes log a minus x. So if y was minus 3 to the x, let's say, then inverse is equal to log 3 minus x. That makes sense. Two shapes that this function can take. If I have my x-axis, or both axes actually, x and y, let's say my f looks like this. You draw your line y equals x. Whenever you have inverses, it's useful to do this. And my inverse becomes something like this. Notice that nothing happens here. If this function will tend towards this axis, this one will tend towards this axis here. Another shape it can take is if it's something like this. and I have an exponential where a is less than 1. So this is f. I draw my line, just use consistency. Draw my line y equals x. And what will the reflection on this look like? It'll look something like this. So that's just two you can remember. If it's the exponential looks like this, the inverse will look like this, and if the exponential graph looks like this, then the inverse looks like this. Now I'd just like to, now that we've got the basic understanding of log rules and how they link with exponential graphs, I just want to give you some log laws that could be helpful. So log laws. Let's say, here's our first log law. We have log base a to the x plus log base a y. This is equal to log base a x times y. What do I raise a by to get to x? Plus what do I raise a by to get to y? Will be what must I raise a by to get to x times y. That's how you can read it. The second log law is very similar. Because log base a x over y. So you can see this is just if the plus does a multiplication, then the minus turns into division. A third log law, let's say log base a x to the power of m. This is going to be the most useful one. You can take the m to the front and it becomes m log base a of x. This is the one you're probably going to be using the most, so let's put a little star next to it. This is very important. Log base a x to the power of m becomes m times log base a to the x. For fourth one, log base a x is equal to, this is known as the change of base log law, over log b of a. Now, I can choose any b for this to work. Usually we just use 10 because 10 is just the generic default log. But basically what I'm saying is the log with any base a and x, I can write it as log with any base I choose for b, x over log that same base. This b can be anything I want, but the condition is that this b must be the same as this. Obviously, these two must be the exact same of a. So these you really just have to memorize. There's no tricks or anything. So I have a question here. I'll leave these here so you can do that, but I'd like you to just do an example, and then once you finish it, I'll do it as well. It's if 2x is equal to 13, use log laws to solve for x. And a little hint is a little hint, log both sides. All right, awesome. So what I do here is I just log both sides. Now I'm just picking 10 as my base just to make it easier. So I can say log 2x is equal to log of 13. And now the reason why I don't have here, why I don't have log base 2 of x is when you're solving questions where you have to log both sides, you're you're applying the function log to it. Now the function log has this base. We just when we're solving equations like this, we just make it 10. So what we have is log base 2x. This is what the log of both sides mean because the log function is actually a log of your input x. So your base actually doesn't change of your log. If you're logging both sides, as long as your base is the same, it doesn't matter. So this becomes log of 2x is equal to log of 13, just logging both sides. Now this becomes from this law here, this log here that I said you're going to use probably the whole time, always. This becomes x log 2 is equal to log 13. Now x is just log 13 over log of 2. Now this is actually just something you can type into your calculator. On your calculator there's a button for log and you just simply write log 13 over log of 2 and you get 3.7. And this makes sense because 2 to the power of 3 is 8, 2 to the power of 4 is 16, so it's somewhere between the two. This makes a lot of sense. All right. Now I just want to just give a couple of tricks. Log base a of a is equal to 1. And you can think, why is this true? This is just a useful identity. You don't necessarily need to know this, but this is just interesting. A, what log a means, what do I need to raise a by to get to a? And obviously a to the power of 1 is equal to a, so your answer is just 1. If I have also log base a of 1, this is equal to 0. And this is because a to the power of 0 is equal to 1. Remember that anything to the power of 0, it will just be 1. So what do I raise a by to get to 1? And my answer is 0 because a to the power of 0 is equal to 1. Also, now that we have that out of the way, that is all the theory. So for the rest, I have a couple past papers that we can do. So let's start with this one here. I'm just going to grab it. I'm going to put it here and I'm going to place it. I just want to make sure that this is the, yeah, all right. So just going to give you some time to do this, then we'll mark it afterwards. For now, just do 5.1 and 5.2. Give you like 6 minutes. Okay, already done. All right. So 5.1. So questions like these, once again, I like to read through all the information first. So they said I have a graph of g of x, 2 over x plus p plus q. Now, this is a hyperbola just because of the form that is in 2 over x minus p plus q. And fx is equal to log 3x. So this is the inverse of an exponential. Now they say y equals minus 1 is the horizontal asymptote of g. So what this means is that q will be equal to minus 1. We can already know that the asymptote of the graph of g will become q for a hyperbola, because the hyperbola is 2 over x minus the vertical asymptote plus the horizontal asymptote. So I can already say that q is minus 1. B 1.0 is the x-intercept of f. So over here I see that f cuts the x-axis at 1. A t.1, let's look at that here, is a point of intersection between f and g. So I'm saying this exponential inverse and this hyperbola cut at the point A, t1. Now, the vertical asymptote of g intersects the x-axis at E and the horizontal asymptote at D. So basically this. It's telling me that this is where the asymptotes are. Now they're saying that OB, this distance here, is equal to, this looks terrible. Oh shit. Let's just leave it there, whatever. This distance here is equal to the distance here. OB is equal to BE. We'll get back to this later. So Q is minus 1, right on the range of G. From the hyperbola, we know that if we look at G, where does the function not exist? Hyperbolas don't exist at y equal to q. That is just something we know, that the hyperbolas don't exist at the horizontal asymptote. So the range is y is an element of R, real numbers, but y cannot be equal to minus 1. This hyperbola exists for all values of y except when y is equal to minus 1. That is what this statement reads. Y is any real number, but y cannot be minus 1. So in essence, you can also write it as y is an element minus infinity to minus 1 and minus 1 to infinity. This would be the same thing. This means the same. You can either write it one of these two ways. Now, 5.2, determine the equation of G. Now, we've already said from information that Q is equal to minus 1. So, now we're going to be using this formula here. What do we need? We have that Gx is equal to 2 over x plus p minus 1. We've just subbed in Q as minus 1. So this is now our higher level equation here. We've added a few things in. Now, what else do we need for a hyperbola? We have the horizontal asymptote. We need the vertical asymptote. They tell us here that OB is equal to BE and that this line x is equal to E is our vertical asymptote. So if this point is 1, this distance is 1, and that means that this distance is 1 because OB is equal to BE. So what does it make this entire distance? It makes it 2. So I have that the vertical asymptote is that x is equal to 2. So what I have, I just substitute in is equal to 2 over x minus 2 minus 1. Now, something I do not like about the mathematics department is that we've standardized that gx is a over x minus p plus q. But then in the question, they say x plus p plus q. If you remember from last week's lecture, we said that a hyperbola is fx is equal to a over x minus p plus q. And we said what happens when p is negative and p is positive if p is the actual intercept. So my advice to you is, if you're familiar with this equation of it, using this will get you more marks than using this. If this with the plus confuses you, because it confused me, what I did is I just used this and got my marks and said, all right, you do you, I'll do me. This, you can use this or you can use this, whichever one makes sense to you. So I prefer this x minus 2 method. So here's your answer. Whichever one works for you. Now let's just give you a couple minutes to 5.3 and 5.4. Right. Let's do question 5.3 quickly. 5.3. Calculate the value of t. So let's go back to information. The point A, t1 is here. So they're saying if the x coordinate is t, the y coordinate is 1. So we have the graph of g cuts the point y is 1 at x is t, and so does f. So we can either use g of x or f of x. My advice to you is, since we solved for p and q in 5.2, it's safer to use log base 3x, because if this equation is wrong, our answer for t will be incorrect. So what we have is we have that log base 3, see, point t1 x is equal to 1. Now, what this means, what do I raise 3 by to get to x? It's 1. So 3 to the power of 1 is equal to x. So 3 to the power of 1 is equal to x. And this means x is just 3. Well, but since they say the point x is just t, we just have t is equal to 3. You could have just said log base 3 of t is equal to 1 and solved perfectly fine. I just prefer to, I like the methodology of a is in terms of x and y. So if y is 1, I can solve it by saying x comma 1. This just helps me with other questions as well. So I have here that t is equal to 3. Now question 5.4, they say, write down the equation of the inverse of f in the form y is equal to something. So we have fx is log base 3x. Let's write that down first. Equals log base 3 of x. Now, what is the inverse? There are two methods you can do it. You can just say, all right, if fx is log base 3 of x, that shortcut formula says that inverse of f is just going to be 3 to the x. Or you can do the other method where you say swapping x and y. You have x is equal to log base 3y, and from this you get that y is equal to 3 of x, 3 to the x. But now they are specifically in the form y is equal to. So leaving it like this is not good. We need to specifically write y is equal to 3 to the power of x. Something that can help you with not losing marks like this is, once you think you've solved the question, go back to it, read it, and say, have I written down the equation of the inverse in the form y is equal to? That's how you can check. Now, I'll give you a bit of time to do 5.5 and 5.6 as well. All right, let's go to, let's first read 5.5 and say, for which values of x will the inverse of x be less than 3? So what they're asking us is, where will 3 to the power of x be less than 3? So we just write 3, not even writing, 3 to the power of x be less than 3. Now, whenever you have questions where they say, when will a function be less than a certain value? That implies that there'll probably be a value where they're equal, right? So what we're doing is we're actually solving where it is equal to and just taking that value and making it less than it. So what will x be for this value to hold? Well, obviously 3 to the power of 1 is just 3, so x is 1. So for what values of x will 3 of x be less than 3? Well, if 3 of x is equal to 3 when x is equal to 1, and they're asking for the inverse. If the function looks like this, then this is going to look increasing, right? Then I can just say if 3 to the power of x is equal to 3 when x is 1, then 3 to the power of x is less than 3 when x is less than 1. And we can check this. If x is minus 1, it becomes 3 to the minus 1 is less than 3. And this is true because this is 1 over 3. This is correct. So we have this equation here. 3 to the power of x is less than 3 when x is less than 1. This is the line that they're looking for. This is giving you your marks. So they're probably going to give you a mark here for solving for this, and then they're going to give you a mark for this statement here. Now, determine the point of intersection of the graphs of f and the axis of symmetry of G that has a negative gradient. All right, so that's a lot of wording. Let's unpack this. The point of intersection, so where the two things meet, where they cross each other. The graphs of f and the axis of symmetry of G that has a negative gradient. All right, so what do we notice about G? G is a hyperbola. What do all hyperbolas have? They have two axes of symmetry. If this is your asymptotes, there will be two axes of symmetry. This one here, and one like this. You'll see that the hyperbola is symmetrical about both these lines. If this were to be a straight line, what would this gradient be? Would this gradient be positive or negative? Well, it's a straight line going upwards, so this is a positive gradient. So as they're asking, the one that has a negative gradient, we want to look at this one. Now, something really important is that if g of x is equal to 2 over x minus 2 minus 1, there's a shortcut method to find its axis of symmetry. We said that the axis of symmetry is y equals, you take this, so x minus 2 minus 1 is equal to x minus 3. This is the one with the positive gradient. Or we take minus x minus 2 minus 1. These are your two equations for your two axes of symmetry. When you solve this, we have minus x plus 2 minus 1. We have minus x plus 1. Sorry, minus x. Minus x plus 1. So these are our two axes of symmetry. You find it by taking x minus 2 minus 1, or taking, if you want to erase this, we say minus x minus 2 minus 1. This is your one with the negative gradient, and this is your one with the positive gradient. So what they're really asking is the point of intersection between f and this equation here. F of x is log base 3 of x. So what they're really asking is where is log base 3 of x equal to minus x plus 1. This is what they mean by this. Now, let's notice something. The axis of symmetry, this should actually go through the point 0, by the way. This goes through this point here, right? This point B. B is 1, 0. Let's look at something. Let's say, this is just something you have to just see. Minus, let's define another function x is equal to minus x plus 1. If I were to solve the x cuts for this, let's go x cuts, y equals 0. And you find this by saying 0 is equal to minus x plus 1. And I'd have x is equal to 1. This is really interesting because if we look here, the graph of f of x also cuts the point 1, 0. So since f of x passes through 1, 0, and the axis of symmetry has an x cut at 1, 0, we can say that the intersection is the point B, 1, 0. So again, we have our equation of the negative gradient here. This is the equation of our negative gradient, minus x plus 1. When we solve for the x cut, we see that it cuts the x-axis when x is 1. So when x is 1, this line cuts the x-axis. But what we note is that f of x also cuts the x-axis at 1. So if both graphs cut the x-axis at the exact same point, then surely they meet at that point, right? If two graphs cut through the exact same point, that is the definition of 2 points touching, of two graphs touching. When you can find the same x and the same value, that when you plug it into both functions, gives you the same answer. So this would be your bit of level 4 question. This question here. These are the questions that they throw into papers to separate people from getting high 70s to the people who get high 90s. This is basically the questions that they throw in as just a little, I don't know, just a little curveball for you. So my advice again would be, say, because this question is a bit of a difficult one, let's look at the questions you probably got right. If you got up to this point, look how many marks you've already gotten. You have got majority of the marks for this question. You have 11 out of 14 for this question. What's the point in spending too much time on this question when you already have 11 out of 14 for the paper? So my advice to you, if they ask a question like this and you can solve it, go ahead and solve it. If they throw a curveball at you like this and you're kind of stuck, you're just confused because you don't know how to solve for log base 3 of x is equal to minus x plus 1, that's fine. Move on, come back. This is a bit of a more difficult question, so they don't expect everyone to get this right either. This is just seeing it. Okay, so let's get on to another past paper question we can do. Let me find one. Here's a question we can do. That's the wrong one. Let's do question 6 here. This is also from a past paper. I'll give you a bit of time to do this one. Just do 6.1 and 6.2 for me for now. Alright, cool. So as experiment 1 asks us, it gives us that fx is equal to minus x plus 3. This we know is a straight line. Gx is equal to log base 2 of x. Obviously this is the inverse of an exponential. Now they ask us on the same set of axes, sketch the graphs of f and g, clearly showing all intercepts with the axes. Alright, so we start with f of x, equal to minus x plus 3. This, let's solve for y cuts, make x equal to 0, y is equal to 3. I'm just saying y equals minus 0, just 0 plus 3. Say x cut, y equals 0, 0 is equal to x plus 3. So we have that x is equal to minus 3 here. So we can draw our axes, x and y, and we say that f of x cuts the y-axis at 3 and the x-axis at well, my bad, sorry. This should be just 3. I noticed something. This is just 3 because y equals minus x plus 3, minus x equal to minus 3, and I have x is equal to 3. So x is equal to 3 here. So I can draw my option. Alright, I'm going to do what we all do. I'm going to just change where this is. 3. Right, so this is my f of x. Now, g of x is equal to log base 2 of x. Now, there are two methods you can do. You can either find the original and then kind of deduce what the points are by calculating the opposite. But what I like to do is I just like to say, just use this as a function. I say y cut x equals to 0. And I have that y is equal to log base 2 of 0. Now, here's something that's important. This does not exist. We cannot find a value for y so that this works. Log base 2 of 0 does just not exist. Every log function does not exist at 0. Alright. Now let's look for our x cuts. Y equals 0. Actually, some do, certain ones do, but they're very finicky about it. Log base 2 0, just type this into your calculator. Log base 2 of 0, math error, no solution. So for x cuts, we make y equals 0, 0 equals log base 2 of x. And solving for this, we have 2 to the power of 0 is equal to x, because I'm saying, what do I raise? If I raise 2 to 0, I get x, because this reads, what do I raise 2 by to get to x? And if the answer to that is 0, 2 to the power of 0 is equal to x. So this is that identity earlier, where we said log base 2 of x is equal to y, is the same as 2 to the y is equal to x. And I have that x is then equal to 1, because remember, anything to the power of 0, it will just be equal to 1. So what I have is, it does not cut the y-axis, so it does not go past this point. It doesn't intersect this. I do have, though, that it cuts the x-axis at 1. So if it doesn't cut the x-axis here, if it doesn't cut the y-axis, it looks something like this. That's my graph for g of x. Alright, now let's go to 6.2. Write down the equation of the inverse of g in the form y is equal to. All right, so we have, let's just do it on the side here. If g of x is equal to log base 2 of x, the cheat cut method says g minus 1x is equal to 2 to the power of x, but once again, they say in the form y is equal to. So what we do is y is equal to 2 to the x, and that's your answer for 6.2. We don't have much more time, so let's just finish off with 6.3 and 6.4. Give you a bit of time until 10:02, I think. So just 2 minutes. This is just an explaining question. You don't have to actually solve it. You only solve it in 6.4. Okay, cool. So we have that log base 2 3 minus x is equal to x. What this means by their definition earlier is that 2 to the power of x is equal to 3 minus x. What do we note here? We've just shown that the inverse of g is 2 to the x. So this is g minus 1x. But what we also have is that 3 minus x looks familiar. And it looks familiar because this is f of x. Minus x plus 3 is 3 minus x. So what this means is that solving for log base 2 3 minus x is equal to x, what we actually mean is we're saying where does fx and g minus 1x intersect. So finding the points of intersection between the inverse of g and f of x. So since they asked, explain how you will use question 6.1 to solve the equation. So explaining it means I get it into this form and I say this means that if I can find where f of x and the inverse of g of x intersect, then I can solve this equation. Now they go and say write down the solution. Now I'm just going to show you this. You don't have to show it like this either. What you can just do is you can say 2 to the x is equal to 3 minus x. Now I can just reason this. What must x be so that this holds? Well, if x is 0, 2 to the 0 is 1, 3 minus 0, no. But I can see that if 2 to the 1 is equal to 2, 3 minus 1 is equal to 2, so x is just 1. So that's literally it. That's the solution for the equation. The solution is that x is equal to 1. Your other method which you could do is you could draw the inverse of g, 2 to the x, on this and determine where they intersect. But in this case, this would just be a lot easier. So in the notes that I sent that are attached in the somewhere there, or I have another past paper question worked out for you. So more than welcome to try that one. But I don't think we'll have enough time to do it now. Are there any questions you have of any of the work we've covered today? Is there something you want me to explain more? Something not clear or... All right, awesome. If you want, I can quickly try to do if you have no questions, I can quickly try to, I won't be able to give you time to attempt the question, but I'll go through the question. We still have a bit of time. All right, so here's the question. Question 5 from a past paper. It says h of x is equal to 2x minus 3. Now, notice here that my domain is x is between 2 and 4. They specifically say that x is between these two values. They say also the x-intercept of h is q. Now, determine the coordinates of q. You just say it's the x-cut, so y equals 0. So 0 is equal to 2x minus 3, and I have x is equal to 3 over 2. So q, remember if they ask coordinates, you can't just write this. You have to say q is 3 over 2, comma 0. Now 5.2. So this is just finding where this graph cuts the x-axis. Write the domain of the inverse. All right. This is important. Remember earlier that all x's in f become y's in the inverse. So all the domains from the normal graph become the range of the inverse. And all the range of f becomes domain of the inverse. Okay, so they're saying that we have h of x. I'll just do it here. H of x is 2x minus 3 for x between minus 2 and 4. So the domain is minus 2 to 4. The range I can calculate by just subbing these bounds into my function to find these points here. Surely if x is 4 here, I can find the y value, and if x is minus 2 here, I can find the y value, and then the function will be between these two values in terms of y. So I find h of minus 2, which this will be minus 7, and I find h of 4, and h of 4 will be equal to 5. So if my range of my normal function is y is an element minus 7 to 5, then what is the domain of my inverse? Well, we've said that the range of the function becomes the inverse, becomes the domain of the other one. So domain of f to the minus 1 is x as an element from minus 7 to 5. Now, what's important is these are square in this notation. I can also write it as x less than equal to 5 greater than equal to minus 7. It means the same thing. Now, 5.3, They say sketch the graph of h minus 1 in your answer book. 5.3. If h of x is equal to 2x minus 3, 2x minus 3, and I replace x and y, swap x and y, I get x is equal to 2y minus 3, and I get that y is equal to x over 2 plus 3 over 2. Now, this is just a very basic, just straight line graph. I don't know if I need to, I'll just do it anyway. X and y, x cut minus 3, 3 over 2, and this will look like this. Keep in mind that this is between 2 points because the domain is a thing, minus 7 and 5. So you're sketching it between these two values. Minus 7 and 5. So the trick here is that it's only between minus 7 and 5. Now, let's do 5.4 quickly before time runs out. 5.4. For which values of x will hx be equal to h to the minus 1x? So we have hx is 2x minus 3. You just make 2x minus 3 equal to the inverse. Inverse is x over 2 plus 3 over 2. X over 2 plus 3 over 2. And solving for this, you can write this as 2x minus 3 is equal to x plus 3 over 2. And I can multiply both sides by 2, so I get 4x minus 6 is equal to x plus 3. And I get then x is equal to 3. All right. So that is all I have planned for today. We're exactly finished on time. So thank you for listening. I hope you learned something. I'll see you in the next lesson. Any last questions? All right. Okay.
Thank you.
Awesome.
Thank you so much, Tyron.
Thank
Thank you, everybody. Let's meet again in our next session on trigonometry. Cheers. Bye.